Welcome everybody again. Now today we are going to present the new step on the Chopyn project. On the last session we talked about tonality and what tonality means for music. Okay, it is something that is critical, something that is the essence of the music, and as if you remember well, the tonality is those rules that specify which kind of sounds can be played together at the same time, and those sounds that cannot be played together. I'm going to put this on a full screen. Okay, so now I'm also going to remember which is the journey of this project. At the moment we are still finishing this music architecture, but I have already implemented this LSTM that I will be presenting shortly. And the next step will be to create music based on GANs and to optimize that GAN output based on a genetic algorithm. That will be done between November and December, and finally we will listen to music in December, hopefully. But today I'm going to speak on how to detect tonality from music, how to detect which tonality or which sequence of sounds can be played on a specific sheet of music. Do you remember that the tonality is that thing that gives color to the music? So you can have the same face as here, as in this picture, and you can have actually the same rhythm, the same melody, the same intervals and all that, but it is the color, it is the tonality what gives you that different essence or that different color into the music. As I saw on the last, as we saw on the last presentation, the tonality gives you the importance or let's say this way, or the functionality of each note. For example, imagine each note is a number. For example, here we have 3, 7, and 1. The one at the end is not the same as the one at the beginning, or the 7 is not the same as if I put it on the second position or on the first position. So tonality is saying that 7 is more important than 3, and 3 more important than 1, and that, or in this case, that 3 is more important than 7. Okay, that is what tonality is all about. And the tonality defines the structure of the melody, the structure of the proportion of the music. So in this case we have the tonality for do, and we have to respect all these values that are here. So the let's say the space between the first note and the second note it must be a one tone, and for example the space between the third and the fourth is just half note. So we have to respect there is one note, one space, half space, one, half space. If we have that, this tonality is called major tonality. And if I start on, not in do but in re, I have to make some changes to the notes, and that is what tonality is all about. But on music shows which is the way a musician can extract the tonality from the music, which is the way they act or what they do. Well, it is very simple actually. Very simple if we have the music written. Okay, for example, here if we have this music written here, we can see here there is no alteration, and that means that is a do major. We have one sharp here that is called sol major. We have 2, then is re. We have 3, then is la. Okay, so I have just, as a musician, I have just to have a look to what is at the beginning. Okay, and from there I can infer very easily which is the tonality of the whole picture. Okay, that is the way it is structured. That actually at the beginning it is quite difficult for the students for the very early stage students, because they have to learn some rules to translate these 4 5 sharp or these three flats into the tonality. But yeah, and that is just a rule, okay? But the complexity of extracting tonality grows exponentially if, instead of having the written music, we have just the music played by a musician or the music played by several musicians. If I don't have the sheet music, and then I have to listen to the music, and from that I have to infer the tonality, and that is not that easy. You have to train your ear, you have to train your brain very, very, very carefully to do that, and you have to train very, very intensively. So it's not that easy. So that is what we are doing today. Today we will be extracting the tonality from the music, as this girl is trying to do. But how can we extract the tonality from the music that is played? Is there any kind of strategy that we can follow? Are there any rules that we can implement? Actually, there are three possibilities that are here. We can, for example, take the most common note. If you take the most common note, probably that is the tonic. And if that is the tonic, then you can, for example, infer from that, the tonality. That is true, but there are some cases in where that is not true, and I can give you some example. For example, some piece of Albeniz. In that case, for example, which is very famous for guitar, that piece of music actually, this rule doesn't match. Okay, this rule is not useful for that specific piece of music. Okay, and then we can calculate the chords, the most common chords, and see the most common one, and see if that relates to the tonality. And again, that must have to that let's say that rules is under the assumption that the most repeated chord is just the tonic one, and that cannot be true, because in some cases the most repeated one is that one, the dominant chord, or maybe the subtonic chord combined to the dominant. So that is also not true. So the best idea is to calculate the most likely scale. What does it mean? It means that if I listen to all the notes within a music, and then I say, okay, all those notes are aligned to a specific scales, and I can. The only thing I have to do is just to compare all the possible scales that fits, all the possible scale that fits that music or that piece of music the most, and then we will have the tonality. And this is what we are going to implement today, which is let's extract the most likely scale, and there we will have the tonality. Yeah, so now it is time. It is time to make the programming. Let me change the window right now. Okay. Okay, let me see. Okay, you're seeing it. Okay, great. So now I'm on this. Yeah, you are seeing it already. Yes. Yeah, now. Okay, we are here on the redmusic.py that you can see it on the GitHub, and we are going to focus on this method, which is the get tonality. Okay, the get tonality will be applied to the object called here red, because I'm going to read music from just the name of a file MIDI, from a MIDI file, and from there I have to extract many things, but one of them is just to extract the tonality. And in order to extract the tonality, I have to do this mapping. This mapping here, I did it before, and what that this mapping means. Okay, it is like if I am in do tonality, in tonality of do, then these are the scale. Okay, if this is re, this is the scale of re, and the same for re bemol, mi, mi bemol, fa, and so on. If you have a look to the mi bemol 1, for instance, you won't see any flat there. Okay, any flat. Why? Because what I did is just to convert the different numbers of the MIDI file into the simple notes name, and in case there is an alteration, I give the priority for the sharp. So if there is an alteration, that will be a sharp. So the only thing I have to do is to take care that the re sharp is the same as mi flat. Okay, same for here. La sharp is the same as C flat. Okay, so this is completely needed. Okay, I really need to do all these things. So now I have to also take into account that all my music, all the music that I have extracted from the file is stored inside music df. Okay, this is something that I have done before, and it's so simple that here I read the CSV file and I store this on the music df, and I make some some other things, such as I calculate the name of the note. I mean, I make a mapping between the number of the MIDI notes into the name, and then I also divide the music with most grammatic. That this is something that I'm not going to explain on this video. Okay, so here is the music df here, as you see, and what I'm going to do is just to print it and to print the head as just to see how it looks like. And then what I'm going to do is just to go here and call the method. Okay, just to see that I'm going to read the last name file MIDI. Okay, and this is going to read the DVC clear the loon. Okay, and I'm going to extract the tonality, and it's going to do nothing, but the only thing it's going to do is just to print the head of the file. Okay, so now it is reading the file, okay, of the DVC clear the loon, and now it's going to print the head, okay, and to see which is the music all about. Okay. So this is the structure of the file. We have the start ticks, so it starts at 250 ticks, and this is in milliseconds, and this is the name note, which means that it is a sharp sol on a 4 octave. Okay, and what it means is that this sharp sol must be translated probably into something. So yeah, so we have the method. It works with because it can be called from the main method. But now let's do something else. Let's do something with it. First of all, okay, let's do something like group by name of the nodes. Okay, something like, wait a moment, name nodes. Okay, let's do it this way. Okay, so let's see how it looks like now. So what I'm going to do is just to group by all the nodes Okay, because the important thing here is that we have many different nodes here, so I'm going to just group by per node and to take and collect. Okay, so this is the group by. Probably there's nothing easy to see now, but let's take the total amount of time and that every node has been played, and this is easily done by aggregating, okay, the property dur, which is the duration in milliseconds, and I'm going to just sum them up. Okay, so what I'm going to do is just, okay, let's extract from the whole piece of music. Just give me the name of the note, and the name of the note, it's done, regardless of the octave. So we have octave name note, and we have name note. So this, yeah. So that is what we have, because we have extracted just the head. But I think I can get rid of the head already, because now they're very simple scale. So it is slow because I'm recording this session. Yeah, nice. What we have here is per name node, we have the amount of time that that note has been played. So if we look for the most common one, which is this one, which is sharp do, that is the most common one, and that means that that note, and also the fa sharp, and also the la sharp, and the re sharp is the most common one. If we have a look to this one, which is we have, let's play here, we have do sharp, re sharp, we have fa sharp, la sharp, and we have fa also, and so sharp. We have all these. The only thing we have to do now is, okay, let's see the most common one. Let's see how they fit on this mapping tonality. For example, let's do it manually. We have do sostenido, sorry, do sharp, and do sharp is here and here, and yeah, in many cases, okay. But if we have a look to do, re, fa, la, and sol, let's see which one have do, re, fa, sol, all of them, okay? So we have C, do, re, fa, sol, and la, okay? And we have re, flat, they have do, re, fa, sol, and la. And then we have fa. Fa is one of the most common one, and that is present here in re flat and not here in C, because in C we find mi, not fa. So it seems like this one maps to re flat. Okay, this is what we are going to do now. Okay, so then what I'm going to do is just to rename the columns just to make it easier. Okay, so the milliseconds, yeah, this one will be called cumulative duration. Okay, just this way, just to get confused. Okay, and in order to make it easier, I'm going to order in descending manner, okay, which is something like short values, will sort values of duration, which is the attribute that I have already calculated, and I will be extending equal false. And then in order to get rid of this space here, I'm going to reset index. Okay, and now I think this is going to look much better. Oh, perfect. So we have now the most common one, which is do, sol, la, fa, and the less common one, which is sol, re, si, mi, la. So this is already giving me some, let's say this way, some indication on which is the tonality. And now it is time for, let's create a map. Let's create a dictionary. Okay, something like, okay, let me wrap this into, I don't know why I put some spaces. Okay, here. And let me set the index, because I'm going to create a dictionary where the index is name node and then everything else is the code duration. What I'm going to do is just to create a dictionary to convert the previous array, the previous data frame to a dictionary and see how it looks like, because that will help me to compare this to the tonalities dictionary. Okay, perfect. Have to and yeah, perfect. So now that we have this calculated, I think it's time to get rid of all these brackets. So I'm going to call this, actually this is called histogram, to get rid of the spaces. Let me see if this works well so that I can line this here. Perfect. Okay, nice. So now we have the node histogram, and now it is time to contrast this to the let's say make the join of node histogram to tonality. So we have, let's say this way, let's put this dictionary called tonality candidates, and what I'm going to do now is I'm going to, since I have the cum sum of every node, I'm going to make the intersection with the tonalities and see which is the maximum value of, which is the sum up of every possible tonality. So what I'm going to do is, first of all, join node histogram to tonalities, and then calculate the total amount of time the intersection sounds, okay, and take the maximum. Kind of, I think it's better the argmax, because the argmax is going to give you, which is the node that is giving you the maximum value. Okay, so in order to do this, first of all, we're going to iterate. Yeah. Iters. Yes. So since I'm iterating this thing, which is the tonalities, this is going to give me the name of do, re, res flat, mi flat, and so on. And the tonality scale is going to be the other thing. That is the reason why I'm doing this. So then the idea is I'm going to store for, in this dictionary, I'm going to store, so this is going to put the tonality name, okay, on this empty dictionary, and that is going to calculate the sum, okay, of histogram and get, just to get the iter. Yeah, let me close this, because I'm going to use a compression list. So the idea is I'm going to let's iterate all the tonality scales. Okay. Oh, this is going to iterate every note in every scale, and what I'm going to do is, yes, something like this, which is for every note histogram, okay, which is here, just give me this tone, okay, this tonality, and give me the amount of time, and just sum it up everything. Okay, so now let's bring the tonality candidates and see how it looks like. So this one probably is missing something. Using to dict. Okay. Mm. Okay, now it's working that thing, but not this one. Sorry. Let's see. Okay, perfect. So yeah, this thing doesn't exist. That is tonally this, because this is the name of this thing. Okay. Now it should work. Tonalities is not defined. It's defined here. Tonalities is not defined. Let's see if there is a misspelling error. see, probably there is an error. No. Let's comment that. Let's see if I can print tonalities. Okay, perfect. So this is found. Okay, now. This is something that has to do with now it have no, maybe that one. Okay, the problem was that there were some spaces here, something like this. You see some dots here? Yeah, those dots were causing the problem, okay, because, yeah. So, now here is the funny thing, okay? So now the idea is that this is the result which is giving me the most likely tonality. So we have C flat with 417. We have Mi flat, which is 541, perfect. Yeah, we have that one. Re flat, which is the highest actually, and yes, indeed, this tonality is re flat. Okay, so now the problem is that we have to order this somehow. So I have to order this in a specific manner. So I think the best way to do this is, in my opinion, is first of all, I'm going to print the sorted tonality candidates. Okay. I'm going to sort the key Okay, I'm going to print this and see the result, because this is going to sort, let's say this one. It's going to try to sort that dictionary based on the value. Okay. Okay. Perfect. So now I have to convert this to an ordered dict, and the trick is just to iter this and to take, the first one. And with that, I think I will have yeah, here it is, because the other thing is the other print that I have already calculated, and I have already delayed it. So the only thing I have to do is just to forget about the printing and just return this. So yeah, so now I think what I have to do is print here and see if it works. Perfect. Great. Let's try another one, which is this one, which is in Do. In Do, and it has to say Do. That's the final result. Perfect. And a difficult one, which is this one, which is in Sol flat. So you have to be careful, because if you download a MIDI file, yeah, that's it, perfect. If you download a MIDI file and that MIDI file is not in the original tonality, and you apply this method, this is going to give you not the original tonality, but the tonality of the piece of music. So if the MIDI file is in another tonality, it's going to give you that another tonality. Okay, so this is it for now. Thank you very much for listening and for being there. What we have done is just as remember is this thing, which is calculate the most likely scale for a specific MIDI file, and from there we have inferred the tonality, and now we are able to make the important thing of the tonality is that we are going to make now the learning algorithms such as neural networks, such as LSTM, not to learn the specific note, such as do, re, mi, fa, sol, la, si, but these functions here. So, because the idea is to learn that functionality and not to learn the concrete music of the tonality. So, knowing the tonality now, it is feasible to learn which function has every specific note and every specific chord, and that is powerful tool for learning music. But we will see this on a later lecture. So thank you very much for being there, and see you soon.